Okay, good morning, everyone, and happy Friday. So almost the weekend na. So which means malapit na rin yung lab excerpt. That would be on Monday. So today we'll try to finish the remainder of Module 3. But first, some housekeeping matters. I already finalized my schedule, and my consultation hours would be 1 to 3 p.m. from Monday to Friday. So if you want to, if you have some questions or you want to seek academic advice or wala lang kayo magawa, you want somebody to talk to, so I'll be available from 1 to 3 p.m. Monday to Friday. I created an MS team for my online office, and I already added you guys to that group. So, and then you can just drop by that channel. Tapos meron na dong link for my consultation hours from 1 to 3 p.m. Permanent yon. That's the same link I'm going to use for consultation all throughout the semester. So you can enter that meeting, and then kung wala ako dun sa meeting, just hit me with a chat or an email. So makaka-join ako sa inyo. But I'll try my best to always be there. So kung wala lang kayong magawa or you want to talk about something, so drop by my online office 1 to 3 p.m. every Monday to Friday. And then if none of these hours work for you and you have some important questions, so just let me know and we can set up an appointment. So sabihin nyo lang probably 1 or 2 days in advance. So para makapag-schedule tayo ng custom consultation hours. Okay. Now, going back to our business, so last time we talked about how to minimize the error involved in polynomial interpolation. So we have discovered from your lab last week, or this week, last Monday, that the error term incurred in interpolation has this form, f to the n plus 1 of psi over n plus 1 factorial times omega, which is the product of x minus x sub I, going from 1 to n plus 1, where n is the degree of the maximum degree of the interpolating polynomial you obtain by using the n plus 1 given data points. And we resolved that in order, one way to minimize this error is to minimize this term which we call omega, omega of x natin. And we said there are at least two ways. At least ito yung dalawang paraan na titingnan natin sa Math 174. We will minimize omega with respect to the L infinity and the L2 norm. So we started talking about the L infinity norm or minimizing the L infinity norm of omega and found out na sa class ng polynomials, sa class ng monic polynomials of degree n, ang may pinakamaliit na L infinity norm ay yung Chebyshev polynomials. So our strategy now is to set or to force the issue that omega is equal to the Chebyshev polynomial of degree n plus 1, or the monic Chebyshev polynomial of degree n plus 1. And we can do so if we will choose the x sub i's to be the root, or to be the roots of the Chebyshev polynomial. And we can only do this, or this scheme would be effective if we have a free rein on choosing the x sub i's. So kung meron naman tayong options na pumili out of our own volition kung ano yung mga interpolatory abscissas na gagamitin natin, then in order to minimize the L infinity norm of the factor omega in the error term, pwede nating i-force yung issue na yung omega dapat mag-coincide with the degree n plus 1 Chebyshev polynomial, because if we will be able to do so, then ang maximum or ang L infinity norm ng omega ay magiging 2 to the negative n, right? And we are guaranteed that among the class of degree n plus 1 monic polynomials, this would be the smallest possible L infinity norm. Okay? So kaya ngayon, ang gagawin natin whenever we have the choice and we want to minimize some sort of a local measure of error, pipiliin natin yung interpolatory abscissas to be the roots of the Chebyshev polynomial. And actually, we already know what the roots of the Chebyshev polynomials are. Kasi nga yung Chebyshev polynomial of degree n, siya lamang ay cosine ng n are cosine of x, right? Pero again, we have a recursive definition. Pwedeng t sub n plus 1 of x ay makompute using 2x times the previous Chebyshev polynomial minus the Chebyshev polynomials 2 steps back, right? And our initial conditions for this recursive formula is t0 of x is the constant polynomial 1, and t1 of x is the polynomial x, which we obtain by plugging in n equals 0 and n equals 1 to this cosine definition, respectively. One thing of note about the Chebyshev polynomials is that though they are called polynomials, they're only defined from -1 to 1. Okay. Now, I guess we are now ready to look at a specific example. If we look at example 3.1, we were asked to find the degree 10 interpolating polynomial for this function, arctangent of x minus e to the x plus 0.5 plus x plus 2 using Chebyshev nodes. Well, example 3.1 is a nice example wherein we have a freedom to choose the exabytes. So kunwari, kahit wala tong instruction na Chebyshev nodes yung gagamitin, pwede natin talagang piliin yung mga exabytes out of thin air or kung ano man yung gusto nating interpolatory abscissas. Kasi hindi siya katulad nung halimbawa yung epidemic problem natin from last week na given lamang yung data points na pwede natin gamitin. Dito sa example 3.1, given yung function f, it might just so happen that the function f is too complicated for the specific application that we are working on. Na baka naman dun sa application na gusto nating gawin, kailangan natin mag-integrate, mag-differentiate, o kailangan nating i-manipulate itong function f, but we cannot do so by hand efficiently. So kaya kailangan natin siyang palitan with a polynomial or at least approximate it by a polynomial over the interval -1 to 1. So again, it is explicit na dito sa problem na to, sinabi na gumamit ka ng Chebyshev nodes. So that means the interpolatory polynomial that we will get will have domain -1 to 1. Kasi nga yung roots ng Chebyshev polynomial ay nabubuhay lamang sa interval -1 to 1 kasi yun lang yung domain nila. Maybe I can say a word or two about that later. Pero let's try to implement or to solve this problem using MATLAB. So again, you're not required to use MATLAB, but MATLAB yung gagamitin kong pang illustration sa klase. Gusto ko siyang i-promote, hindi dahil may commission ako from MATLAB, pero dahil may subscription yung university and it is such a powerful tool for mathematicians or applied mathematicians like you guys. So, mas okay na siguro matutunan or maging familiar tayo with MATLAB. Samantalahin natin yung subscription ng university, which is not cheap. So, kaya ganun. All right. So let's start. You will see here that I am taking advantage of the MATLAB code that we used from last week. So kung mapapansin nyo, yeah. So lines 28, lines 37 until line, until the end, hanggang line 67, ito lamang yung kinopy-paste ko lang yung code natin from last time. Kasi yung paggamit ng Chebyshev nodes, wala siyang pinagkaiba kapag ka-fix yung mga exabytes. Ito nga lang, pipiliin natin yung exabytes at kukompute natin yung function values. So that means I don't need to change anything from the actual computation of the Lagrange basis polynomials and the building up or the assembly of the actual interpolating polynomial from last week. Yun nga lang, may additional step. Kukomputing ko yung mga exabytes at saka yung mga corresponding function values. And for that, I need the Chebyshev nodes. And then there are two ways of how to compute the Chebyshev nodes. Probably the easier one, pero hindi yun yung ginamit ko, ay ito, lines 22 until 25. Kung saan, I'll take advantage of the result of remark 3.1.5. Kasi dun sa remark niya, given na yung roots ng Chebyshev polynomial. Ang roots daw ng Chebyshev polynomial ay cosine ng 2j minus 1 times pi over 2j as j goes from 1 until the degree of the Chebyshev polynomial. So, pwedeng siya yung gamitin nyo. And actually, I think this is it is more efficient than what I will show you. Pero yung pagramdahan na ipapakita ko sa inyong method, yung longer method, is ma-review natin paano i-build up yung Chebyshev polynomials and how to work with MATLAB even more. Right? Pero ito yung shortcut. And pwedeng ito yung gamitin nyo sa Excel. Mas madali siya at computationally efficient. Okay? Now, let's look at the code line by line. So kung hindi MATLAB yung ginagamit nyo for the lab exercises, it's still fine. At least dito, dadaanan natin yung algorithm and then the pseudocode. And if you say prefer Python or Scilab or any other programming language, okay din naman kasi kailangan nyo lang i-convert yung syntax ni MATLAB papunta dun sa syntax of your programming language of choice. Okay? Now look at look at line number 1. Remember, sims just tells MATLAB na lahat ng variables after sims ay dapat i-treat niya as a symbolic variable. Hindi niya dapat hanapan ito ng constant value or constant value assignment. So last time, I think I set sims or I set t as my variable or little t dun sa epidemic problem. Binago ko lang siya here into x kasi excess yung ginamit dun sa problem. But not a big deal. And then, right. So dahil sabi dun sa problem, we want an interpolating polynomial of degree 10. So ibig sabihin, yung gusto kong Chebyshev polynomial na gamitan ay 11. Bakit degree 11 na Chebyshev? Kasi para makakuha ng degree 10 interpolating polynomial, kailangan I'll choose 11 data points. Kasi remember, the maximum degree is 1 less than the number of points used. So kung degree 10 yung gusto ko, I'll try degree 11, Chebyshev polynomial, para mabigyan ako ng Chebyshev polynomial ng 11 roots. At yung 11 roots na yon, mataas yung possibility na magbibigay sa akin ng degree 10 interpolating polynomial. Okay? So that's why I set here degree equals 11. And then line 8, nag-declare ako ng another symbolic variable. So here I let big T or capital T to be a symbolic variable. Saan ko gagamitin si T? Gagamitin ko si T to be the vector vessel ng mga Chebyshev polynomials. Kasi remember, may dalawang paraan tayo para mag-define ng Chebyshev polynomial. Either the cosine definition or we use the recursive form, the recursive definition. So pag ang gagamitin ko dito yung recursive definition, and for the recursive definition, kailangan ko si t sub n at saka si t sub n minus 1 para ma-define si t sub n plus 1. So para ma-compute ko yung bagong Chebyshev polynomial, kailangan ko yung dalawang latest Chebyshev polynomials. So kailangan i-keep track ko bawat isang t sabay. And that's what the variable t will be for. Diyan ko i-store lahat ng Chebyshev polynomial. At dahil yung mga Chebyshev polynomial, symbolic expressions sila, so kailangan i-declare ko si array t o si vector t to be a symbolic variable. Okay? And then now, kailangan ko yung initial values ng mga Chebyshev polynomial, or yung initial Chebyshev polynomials. So this is a little bit of a bummer for MATLAB. Hindi naman bummer, pero para dun sa definition natin ng Chebyshev, medyo mag-adjust tayo ng index. Kasi remember, nag-define tayo ng Chebyshev starting from t sub 0. Ito yung degree 0 Chebyshev polynomial, which is 1. And t1 is the degree 1 Chebyshev polynomial, which is x. Kaya lang, yung indexing ni MATLAB, nag-start siya sa 1. So kung meron kang vector, ang una niyang element ay nasa address 1. So you see here, I need to let the first entry of t, which is called t of 1, to be equal to 1, which is the degree 0 Chebyshev polynomial. Then yung t2, siya yung degree 1 Chebyshev polynomial, which is equal to x. Hindi pwedeng t0 kasi walang 0th entry yung vector t. Kay MATLAB yung indexing nag-start ng 1. Okay? So merong konting adjustment. So ibig sabihin, yung capital T of n, siya yung degree n minus 1 Chebyshev polynomial. So kailangan natin mag-adjust ng isa dun sa index. Okay? But I don't think that's a big problem. We just need to be consistent about it. So lines 12 to 14 computes the actual Chebyshev polynomial via a for loop. So I'll start the recursion now from 3 kasi meron na ako ng first two elements ni t, yung unang dalawang Chebyshev polynomial. So I'll start my for loop at 3, and then I'll end up with degree plus 1. Kasi remember, yung nth entry, yung pang n na entry ni t, ay degree n minus 1. So kung gusto ko ng degree 11 Chebyshev polynomial, kailangan kong kunin si t of 12, right? Kasi yung index, mas mataas ng isa kaysa dun sa degree makukuha kong polynomial, right? So here, I will, in the for loop, I am setting the value of the ith entry of t to be equal to 2x times the previous entry of t, which is your degree what? Degree I minus 1. No, sorry, degree I minus 2 Chebyshev polynomial minus the degree I minus 3 Chebyshev polynomial. Okay. And I will do this hanggang makaabot ako ng degree plus 1 para makuha ko yung T12, which is the Chebyshev polynomial of degree 11. Okay. So if we run this code, right, so run ko lang tong part ng code para makita natin yung mangyayari. Okay. So now everything is computed. Wala namang error notif dito. So nag-run naman siya ng maayos. Then if you want to see what is the degree n, what is the degree 11 Chebyshev polynomial, so let's just look at t of 12, right? Kasi sabi natin laging mas mataas ng isa yung index kaysa dun sa degree. So the degree 11 Chebyshev polynomial should be the 12th entry or the last entry of the vector t. Now you'll see ito yon. Itong mahabang expression na yan. Pero maybe it's better if we will look at it in a VPA fashion. So para makita yung decimal form niya, pwedeng gawin nating VPA of ANS. Hindi pa rin pala simplified. Siguro, tingnan ko kung masisimplify niya. Okay. Yeah. So at least dito, kita natin na ang first entry niya ay 1024 times x to the 10th times x. So that's going to be 1024 x to the 11th, which is what we wanted kasi gusto natin yung degree 11 Chebyshev polynomial. And here you see that the coefficient, the leading coefficient is 1024, which is what we expected because by remark 3.1 we said that the degree n Chebyshev polynomial will have leading coefficient 2 to the n minus 1. So this is a degree 11 Chebyshev polynomial, so its leading coefficient should be 2 to the 10th, which is 1024. So it seems that so far everything is in order. So we can continue. So sa line 16, yung pang 12 entry ni t, which is basically the degree 11 Chebyshev polynomial, inassign ko lang sa variable tn. Ito pala pinadisplay ko yung tn, but that's fine. Kasi di ba yung susunod nating mga solutions magre-revolve lang naman sa degree 11 Chebyshev polynomial kasi yun yung kukunan natin ng roots para gamitin as our nodes. Okay. Hold on guys, excuse me for a minute. Okay. Now, para makuha yung mga interpolatory nodes, kailangan nating kunin yung roots ni Chebyshev polynomial of degree 11. Okay? Remember from last time, from last week, we look at ways on how MATLAB can compute the roots of a polynomial. So kaya lang kailangan dun sa syntax ay yung vector consisting of the coefficients ng polynomial na gusto nating hanapan ng roots. So that's why in line 19, I asked MATLAB to compute the or to find the vector consisting of the coefficients of Tn, right? So remember, ang syntax ay sim to poly. Ibibigay niyo lang sa akin yung vector consisting of the coefficients of Tn, starting from the leading coefficient down to the constant term. So if we run this, so we'll get this. So ito yung coefficient matrix, coefficient vector. Leading coefficient is 1024, so ito yung x to the 11th plus 0 x to the 10th minus 2816 x to the 9th all the way down to negative 11x plus 0. Right? So yun yung mga coefficients ng Chebyshev polynomial of degree 11. Ito rin yung makikita nyo sa notes kasi dun sa notes nakasulat dun yung t sub 11. So mado-double check nyo siya. And then in line 20, I asked MATLAB to compute the roots of the Chebyshev polynomial. So ang syntax ay roots of coef. Tapos inassign ko siya sa variable na Chebyshev roots. So if I run this, we'll get the roots of the Chebyshev polynomial. Ito yun. So ibig sabihin, sa interpolation natin, ang mga exabytes na gagamitin natin ay 0, negative 0.9898, negative 0.1996, and so on. And again, MATLAB in the command only displays on the command window, I think 4 decimal digits. Pero pag tiningnan nyo siya sa workspace, double-click nyo yung coef, not coef, Chebyshev roots. Makita nyo yung, actually hindi nyo rin pala din-display. Kahit ini-display niya lang yung 4 decimal digits, ginagamit niya yung maximum precision sa pag-store ng mga data. So if I click on, say, the second entry, tapos copy, tapos i-paste ko siya dito sa command window, makikita nyo yung maximum precision na ginamit. So ilan ba ito? 2, 4, 6, 8, 10, I think it's 15 or 16 decimal digits, significant digits yung ginamit niya. So if you want to refer to, say, the 10th element of, or the 10th entry of Chebyshev roots, type nyo lang yung Chebyshev roots of 10. Bibigyan nyo yung 10th entry ng vector Chebyshev root. Wrong spelling pala. Case sensitive nga pala si MATLAB. So ginamit ko capital R, so dapat capital R. So you get 0.5406. All right. Any questions so far? How's it going? Okay pa naman? Okay. Now, as I've mentioned, this is the long route. Kaya lang gusto ko tong gamitin to illustrate to you para ma-review ano yung mga syntaxes na pwede nyo gamitin in the future, at saka para makita natin yung mga Chebyshev polynomials, right? Pero again, you can take advantage of remark 3.1.5. This is a more efficient way of computing the roots of the degree 11 Chebyshev polynomial. Hindi mo na kailangan makita yung actual itsura ng Chebyshev polynomial kasi given na sa atin yung formula or na-derive na natin yung formula para dun sa mga roots niya. Okay? So that could be a nice alternative. Now, puntahan na natin yung main bulk ng program, which is the derivation routine for the algebraic interpolating polynomials. Remember dun sa code natin from last time, gumamit ako ng, actually, pangit pala yung ginawa ko dito kasi ginamit ko ulit yung vector t, pero i-overwrite lang naman niya yung previous t. Saka okay lang na ma-overwrite yung t kasi hindi ko na naman kailangan yung Chebyshev polynomial, yung mga Chebyshev polynomials stored in the vector t. So I can reclaim the variable t and assign it to another value. So kaya lang usually ayaw natin na mag-overwrite ng data kasi baka later gagamitin pala natin yung mga Chebyshev polynomials which is stored in a vector t. Kaya lang, ngayon ko lang napansin na last time pala, vector t yung ginamit natin para dun sa mga interpolatory abscissas, kasi hindi ko na siya pinalitan. So I'll keep it here. Or actually, yung pala yung maganda kay MATLAB, pwede natin siyang ipabago. So pwede ko itong gamitin na tawagin na variable na nodes. Tapos if you press Shift Enter, papalitan niya lahat ng t into the variable nodes. Kaya lang, ano yung mababago? Babaguhin niya yung nasa buong program. So kung babaguhin ko to, lahat na ng t naging nodes para hindi ko ma-repeat yung variable t, pero malamang in-overwrite niya rin yung t sa taas. Oo nga, no? In-overwrite niya rin yung t sa taas. So, yeah. Balik ko na lang siya sa t. Okay, yeah. Pero isa siyang shortcut. Kayang baguhin ni MATLAB lahat ng nandun sa lahat ng variable dun sa code. Now, just be careful. Remember dun sa code natin from last week, ang interpolatory abscissas ay inorganize natin into a row vector. So isang row tas maraming columns. Kaya lang, yung Chebyshev roots, kung tingnan nyo sa workspace, nakalagay dyan ay 11 by 1 na double precision variable. So 11 rows and 1 column. Hindi siya compatible dun sa pagkaka-design natin nung AIP routine from last week na nagko-consider ng isang row tapos maraming columns para sa interpolatory abscissas. So in order to get that, I'll just need to get the transpose ng Chebyshev roots. Remember yung transpose ay kung meron kang matrix ij, so yung transpose niya, pagpapalitin niya lang yung row and column number. So to get the transpose of a vector or a matrix, lagyan nyo lang yung, sulat nyo lang yung matrix name, tapos followed by dot apostrophe. Etong dot apostrophe will give you the transpose of the vector Chebyshev roots. So if I run this, so si vector t ngayon ay papalitan ko ng transpose ni Chebyshev roots. Okay, and if you look at your workspace, si vector t na ay 1 by 11 double precision vector. Okay, which is fine, which is now compatible with how we designed the AIP derivation routine from last week na meron kang row vector. Okay. Now, meron na tayong interpolatory abscissas. So, susunod ay compute natin yung mga function values. Kasi last time, given yung table of function values, ngayon kailangan natin siyang computein. Now, that is done in line 34. And this is the nice thing about MATLAB. Hindi ko na kailangang i-for loop yung pagko-compute ng bawat function value. Kasi nga, by default, MATLAB is designed to work with vectors and matrices. So if you look at the first term, atan is the syntax for the arctangent. Tapos tingnan niyo yung input dun sa arctan. Yung input dun sa atan command is a vector t. So ibibigay niya sa akin ay isang vector na ang laman ay yung mga arctangent ng corresponding element ni t. So ang first entry nitong atan of t ay yung arctan ng first element ni capital T. Atan, second entry here would be the arctangent of the second entry of capital T, and so on. And then mas preferred ni MATLAB yung vectorized yung operation. So ang tawag natin dito ay vectorized kasi ang input dun sa function ay isang vector, ang ibabalik niya sa atin ay isa ring vector. Mas efficient siya kaysa sa for loop kaysa sa paggamit ng for loop. Pero sa atin, ilan lang ba yung points natin? 11 lang yung points natin. So it doesn't matter. Insignificant yung masasave na time kung vectorial yung gagamitin. Pero if you have, say, 10 million data points, mas madali kay MATLAB na gawin siya in a vectorized fashion rather than in a for loop. Okay? Now, ano nga yung function natin kanina? Yung function ay arctangent of x minus e to the x plus 0.5. So, e raised to something in MATLAB has syntax exp of something. So ito yung e to the something plus 0.5. And then ganun din. Pwedeng vector yung input tapos plus 0.5. Okay, plus x plus 2. So yeah. So if you run this, bibigay niya yung 11 data points na gagamitin natin for our interpolation. And I think with this, we are ready to run the interpolatory routine. Pagkuha ng Lagrange basis, tas yung assembly ng function p o ng interpolating polynomial p. Okay, let me hit F9 to run that main part of the code. Luckily, no problem there. And then let's ask MATLAB to show us ano yung interpolatory polynomial. Okay. So if I want to display the interpolatory polynomial, ito siya. Ang haba, kasi degree 11 nga naman. Pero hindi ko siya mabasa ng ganitong form. So let me use VPA again. VPA of simplify P. Ito pala, pag sa command window, pwede yung pindutin yung up button. So pwedeng sulat niyo yung first few characters of the command you want to perform. Tapos, kung sure kayo na na-run nyo na siya before, pwedeng type niyo yung first few characters, tapos sa command window, tapos press up or down. So makikita nyo yung pinaka-recent na mga similar commands na nirun nyo dun sa command window. So narun ko to kahapon dun sa isang klase. So yung VPA simplify of P, tingnan natin. Ito yung simplified form ng interpolating polynomial. Okay. Actually, hindi pa pala ito masyadong simplified kasi meron ka pang 0.49 x times 1.59 times x to the times x and so on. Naka-corners display pa yung polynomial. So if you want to check yung sagot dun sa vertex, pwedeng tingnan natin yung coefficients nitong polynomial p. So remember the command to see the coefficients is sim to poly. Nung gusto nating hanapin yung coefficients. And you will see these are the coefficients. So sim to poly of p. So yung coefficient ng x to the 11th is something close to 0. Pag nakita nyo yung display ni MATLAB as 0.0000, probably hindi siya eksaktong 0. Malapit lang siya mag-0. So 0 lang yung first 4 decimal digits niya. Pero how can we see the first entry or the first coefficient? Maybe I can use VPA ng ans of 1. Okay. So VPA ans of 1, kukunin niya lang yung decimal representation ng first entry ng vector ans. Vector ans kasi hindi ko na-save yung sim to poly of p into a variable. So by default, MATLAB will assign it to ans. So kaya ans yung ginamit ko dyan. Tapos kung mapapansin nyo, ito rin yung coefficient ng x to the 10th dun sa vertex. That means so far, we have the same interpolating polynomial as the vertex, at least insofar as the first coefficient is concerned. And you can double check the rest of the coefficients, parehas sila ng sagot. Okay. Okay, and then let's see. Usually magandang merong graphical representation yung result nyo. Kasi yung interpolating polynomial, it doesn't mean too much to us. Lalo na kung malaki yung degree, hindi natin siya kaya i-interpret. So mas okay to give a visual representation for your result. So here we'll take advantage of MATLAB's fplot command. Kaya niya mag-plot ng symbolic variables. So line 55, gagawa lang siya ng figure window. Line 56, ipa-plot niya yung polynomial p over the interval -1 to 1. Tapos, gusto kong i-compare siya dun sa actual function na gusto nating i-approximate at i-compare silang dalawa. So, if I want them to be plotted on a single command, on a single figure, right? So, after nung first plot, pwede ako maglagay ng command na hold on. Ibig sabihin, hindi i-overwrite ni MATLAB yung previous figure. Idadagdag niya lang on top of the previous plot yung graph na nasa line 58 o yung ipapagraph ko sa line 58. Kasi pag wala yung hold on, ang gagawin ni MATLAB, ipa-plot niya si P, pero ipa-plot niya si A tan, papalitan niya yung previous graph. So ibig sabihin mabubura to. So if you want them to be on top of each other, you need to put the command hold on. Okay? Tapos ipapaplot ko yung, right? Ito yung polynomial, ito yung function f dun sa vertex. Now, I used x here. Pwede kong gamitin si x kasi yung x is defined as a symbolic variable in line number 1. It's perfectly fine. And let's look at how these two graphs look like over the interval -1 to 1. And remember, -1 to 1 is our interpolatory interval kasi nandun yung mga roots ng Chebyshev polynomial. So if I run this part of the code, medyo kagigising lang din ni MATLAB ko kaya medyo matagal. Here we go. Okay. So ito yung plot ng dalawang function over the interval -1 to 1. And you see na almost equal lang silang dalawa. I know for a fact na dalawa na yung graphs na to kasi ang default color ng isang graph kay MATLAB ay blue. Tapos kung multiple graphs sa isang figure window, iba-iba yung kulay. So the first graph would be colored blue, the next graph would be colored orange, and so on. So alam ko nag-overlap sila, at least on the interval -1 to 1, kasi orange lang yung nakikita ko. Okay. Now, medyo hindi siya insightful or baka hindi ako maniwala na ganun kaganda yung interpolatory interval. So maybe I can also look at the absolute error. Siguro pwede kong ipa-plot kay MATLAB yung absolute error. So, and that's what I have line 60 to 62. Figure, gagawa uli ako ng bagong figure window. Kasi pag nakalimutan kong ilagay si figure, ibig sabihin itong susunod na plot ay i-graph ni MATLAB dun sa previously available figure window. So pag hindi ko sinulat yung line 60, mau-overwrite itong figure window na na-create natin sa line 55. Mawawala itong graph na to. So ayoko siyang mawala for now. So nagawa ko ng bagong figure window. And then now I ask MATLAB to plot the function which is the absolute value of p minus f para makita ko ano yung itsura ng error function sa interval -1 to 1. Okay? And then I can call this or I can put a title yun sa mga MATLAB figures. So halimbawa ito ay ang title na nilagay ko ay absolute error plot. So whenever you want to input a text or a character or a set of characters in MATLAB or a string of characters, lagyan nyo lang ng apostrophe. So I can run this part. F9. Okay, there we go. Ito yung absolute error plot. And you see na maganda yung approximation because over this interval -1 to 1, ang maximum error lang ay about 1.4 times 10 to the -5. So kaya pala, dun sa una nating plot, when we compare the graphs of P and F, halos wala silang pinagkaiba. Right? Nag-overlap sila halos kasi pala yung absolute error between them is not more than 1.5 times 10 to the -5. Kaya halos nag-overlap na sila. Okay? And yeah, and luckily here we know what the function f is. Pwede nating ma-compute yung actual error. Okay? Hold on again, guys. Excuse me for a minute. Okay, now I'm back. Pero okay, so that's what it is. Now, remember dun sa error term na na-derive nyo sa klase, yung error term na yun ay valid lamang over the interpolatory interval. So, ibig sabihin, nag-guarantee lang natin yung error ay magiging bounded by the maximum value ng n+1 derivative over n+1 factorial times omega. So, alam natin ganun kalaki yung error, ganun kalaki yung posibleng pinakamalaking error. But outside of the interpolatory interval, wala na tayong control kung ano mangyayari dun sa error. And true enough, if you look at, say, I'll expand the plot of P and F. Halimbawa, ipag-graph ko siya from -1.5 until 1.5. Tingnan natin kung ano yung behavior ng polynomial. Okay, so these are the graphs of P and F again on one figure window. And you see na nag-start na silang mag-deviate. Kung makita nyo dito sa tail left portion, medyo naghiwalay na yung dalawang graphs. So medyo nagkaroon na rito ng mas malaking error, possibly than 10 to the -5, as well as on the right end, nagsimula na rin silang maghiwalay. So kung palakihin pa natin yung interval, kung saan ko siya ipa-plot, say, from -5 to 5, kasi ipa-plot ko uli siya, ito na yung itsura niya. So from -5 to 5, makikita nyo na yung napakalaking difference ng dalawang function. So the blue function is the function, ano nga ba yung blue? Inuna natin yung P, so siya yung interpolating polynomial. So yung interpolating polynomial natin, yung P, napakalaki na nung values niya from -5 to 5. It reaches something like to the tune of 3 times 10 to the 4th, which is understandable kasi degree 10. So, posible talaga napakalaki ng function value nung polynomial kapag yung xi may magnitude na greater than 1. And true enough, kung makikita nyo, magkaiba na nung interpolating polynomial at saka nung function to be approximated. It seems that the function that we want to approximate ay hindi lumalumpas ng 1 times 10 to the 4th kasi halos flat line siya dito. Hindi natin makita yung deviation. Siguro pababain ko, wag minus 5. Gawin natin say minus 2 to 2. Para makita natin yung mas subtle na differences in their behavior. Okay, there you go. So from negative 2 to 2, ito na, magkaiba na yung itsura nila. All right. And this is understandable. Again, this can be explained by the validity sort of the interpolatory polynomial. Remember that again, the error is guaranteed to be bounded over the interpolatory interval. When we say interpolatory interval, that is the interval comprised of numbers between the smallest and the largest interpolatory abscissa. So dun sa ating, dito sa ating problem, ang interpolatory interval natin ay negative 1 to 1 kasi yung roots ng Chebyshev polynomial ay nandun sa negative 1 to 1. Alright? So walang root na lumalampas ng negative 1 to 1. So yung interpolating polynomial natin ay valid lamang from negative 1 to 1. Outside of that interval, hindi na natin alam kung bounded ba yung error. So that's why, kaya ang tawag sa kanya ay interpolatory interval. Interpolation, so ibig sabihin interior. Interior points lang yung pwede nating gamit or para dun lang sa interior points yung pagsasubstitute natin ng function values. So say if you want to know what is or to get an approximation for the value of the function f, say at 0.5, so pwede nating gamitin yung polynomial p para ma-approximate yung f of 0.5. Kasi si 0.5 ay nasa loob ng interpolatory interval. Let's say if I want to get the function value at say, or an approximate for the function value at 10. So hindi ko pwedeng gamitin yung p of 10 para i-approximate yung f of 10. Kasi si 10 ay nasa labas ng interpolatory interval. And again, I cannot do that because I don't know what the behavior of the error is outside of the interpolatory interval. So probably you can say this is a drawback of using Chebyshev polynomials kasi paano kapag yung interpolatory interval ko ay hindi negative 1 to 1? And I guess that's what you will discuss in the labs on Monday. Paano i-scale at i-translate yung roots para mapalaki yung interpolatory interval. So yun yung gagawin niya sa lab on Monday. Okay, let me see. What else do I want to say about this? I think that's it for this example. Any question? Nakukumbinsi ko na ba kayo na gumamit ng MATLAB or gusto niyo pa rin yung luma yung programming language? Again, it doesn't matter. Masanay lang talaga ako dun sa MATLAB. So, bakit smiley yung reaction? Or late ko lang nakita yung smiley reaction? Okay, let me go back to the worksheet. Okay, so dahil hindi natin matatapos yung worksheet 3, nagpa-poll ako sa mga lab instructors niya. Pinapili ko sila. Either i-discuss nila yung remainder ng module 3 sa lab or konti lang yung i-discuss nila. Yun lang translation ng roots. Tapos ipopostpone na lang natin yung ibang parts ng lab excerpt. Tapos mukhang nanalo yung konti lang yung i-discuss nila kasi popostpone natin yung kalahati ng lab excerpt 1.2. So your lab instructors on Monday will tell you ano lang yung magiging due on the midnight of Monday. Tapos yung about Legendre polynomial, so i-move natin yung deadline para sa lecture natin on Wednesday, we'll talk about Legendre polynomials kasi adjust natin yung deadline ng corresponding problems in lab exer 1.2. Okay. And actually, it's still good kasi may buffer naman tayo sa semester. Meron tayong, I think, 2 weeks na buffer. So, hindi naman tayo kailangan magmadali. Okay. So if there are no questions about the MATLAB implementation of the program, let me just end with example 3.2. I might need to borrow 3 to 5 minutes over our dismissal time of 9:20. So if you need to leave early, it's fine. Just look at the recording later. But let me finish example 3.2 or discuss example 3.2, which is just an illustration of computing an error bound using whenever using the Chebyshev roots or the roots of the Chebyshev polynomials for the interpolation. Okay. Now here, sabi, gumamit daw ng degree 10 interpolating polynomial para sa y equals e to the minus x over the interval negative 1 to 1. Luckily, the given interval is negative 1 to 1, so pwede natin gamitan yung Chebyshev roots. And actually, we are required to use the Chebyshev roots kasi ang sabi dun sa instruction, degree 10 interpolating polynomial na magbibigay ng pinakamaliit na L infinity error. And again, we learned theoretically from last time na may pinakamaliit na L infinity norm over all interpolating polynomials is that interpolating polynomial obtained by using the roots of the Chebyshev polynomial as their interpolatory abscissas. And then hindi siya doon natapos, pinacompare pa yung error bound para dun sa polynomial na yon dun sa error bound na makukuha nyo if you use equally spaced points dun sa interpolation. Okay. Now let's look at the solution here. So remember, kailangan mo yung roots ng interpolating polynomial. So it might be helpful to either use remark 3.1.5 to get those abscissas or find the roots of p hat 11, whichever works for you. And then if you build up the interpolatory interval, the interpolating polynomial, you'll get this p. And true enough, degree 10 nga siya. And then kukomputin natin yung error bound para sa polynomial na to. Remember that the error bound or the maximum error, actually L infinity error, is bounded above by the, or actually pwedeng sabihin nyo equal, the absolute value ng n plus 1 derivative ni f evaluated at some number c over n plus 1 factorial times omega of x, right? Pero gusto nating mabound to. So kailangan kong makita ano yung worst case scenario, ano yung pinakamalaking posibleng error. So I'll look at a boundary for this. So this would be less than or equal to maximum ng n plus 1 derivative ni f evaluated at the number x over n plus 1 factorial over x's between negative 1 and 1. Okay? Kasi nahanap ko na yung worst case. Ano yung error bound? Pinakamalaking posibleng error. So kailangan i-maximize ko to. Hanapin ko yung posibleng maximum value niya. Okay. And then times the L infinity norm of omega. Oops. And remember, L infinity, the L infinity norm is basically the supremum or the largest possible absolute value of omega over the interval negative 1 to 1. Pero luckily, sa Chebyshev polynomials, alam na natin na yung L infinity norm, kapag gumamit ako ng degree n, Chebyshev polynomial, ang L infinity norm ni omega ay laging 2 to the negative n. So I know that this guy, without any need for any computation, is actually 2 to the negative 10. Ito yung nasa theorem natin last time. The L infinity norm is 2 to the 1 minus n. So here we have degree 11 Chebyshev polynomial kasi si omega ay degree 11. So basically you'll have 2 raised to 1 minus 11. So that's 2 to the minus 10 yung omega. So wala na tayong problema sa pag-compute ng L infinity norm. The problem lies here. We need to get the maximum of the n plus 1 derivative of x over n plus 1 factorial. Wala pala tayong problema sa n plus 1 factorial. Ang n plus 1 yung number of points that were used. So we used 11 points. So meron tong denominator na 11 factorial. Now tingnan natin yung n plus 1 derivative. Ano ba yung function that we wanted to approximate here? The function f is e to the minus x. So ang kanyang derivative, ang n plus 1 derivative niya ay what? I think it is, ang first derivative niya ay negative e to the minus x. Second derivative is e to the minus x. Third derivative is negative e to the minus x. So that means the nth derivative would be negative 1 to the power what? To the power n plus 1? Tama nga ba? Kasi yung first derivative niya dapat negative 1 e to the minus x. Second derivative, no, dapat n. Actually, hindi naman siya magmamatter. Pero, tama ba? Ay, hindi. N plus 1 derivative. First derivative, dapat may negative 1 na factor. So, ibig sabihin ng exponent niya ay parehas dun sa order. Pero remember, kukunin naman natin yung absolute value niya. So, hindi na magmamatter yung negative 1 to whatever power. Kasi ang absolute value niya lagi ay e to the minus x. So, that means, ito, pwede na itong mapalitan ng e to the minus x. Okay? Tapos, gusto nating makuha yung maximum niya over the interval negative 1 to 1. So, what can we say about e to the negative x? Si e to the negative x ay decreasing siya. Kasi yung derivative niya ay negative e to the minus x, which is always negative. So, this function is always decreasing. Dahil decreasing siya, yung maximum value niya over the closed interval would be attained at the smallest value of x. Kaya ang smallest value of x dito ay e to the negative 1. So that means the maximum value of e to the minus x is e to the minus negative 1, so which is e. And that's why here you have e over 11 factorial times 2 to the negative 10. Okay. And when simplified, ito yung sagot. So this means ang maximum error over the interval negative 1 to 1 dun sa pag-approximate natin ng e to the minus x dun sa interval na yon ay about 6.65 times 10 to the negative 11. And you see how accurate this approximation is. Kasi yung absolute error ay hindi daw lalampas ng 10 to the negative 11. At least theoretically. So this is what we call the theoretical error. Kasi ito yung error due to the method itself. Although we are not guaranteed to get this kasi ito yung worst case, pero kailangan pa rin nating i-factor in yung machine precision kung nag-truncation ba o nag-rounding si MATLAB dun sa pagko-compute ng interpolatory polynomial. But if we are working on a perfect machine, the error is guaranteed not to exceed 6.65 times 10 to the negative 11. Yan na yung worst case. Now, if you're using equally spaced abscissas, so ganun pa rin yung first factor, e over 11 factorial, pero kailangan yung i-maximize yung x minus x sabay ay going from negative 1 to 1, na yung mga x sabays are equally spaced points from negative 1 to 1. So 11 points na nag-start kay negative 1 hanggang kay 1 na equal yung increment. And if you do your math 3016 to find the maximum of this polynomial, you'll get something like this. Okay. And then if you multiply these two guys, you get 5.81 times 10 to the negative 10. So ibig sabihin, in the worst case, kapag ka gumamit kayo ng equally spaced abscissas from negative 1 to 1, ang error nyo ay 5.81 times 10 to the negative 10, which is slightly larger than what is the maximum error obtained for using the Chebyshev roots. And this is expected kasi sabi natin yung Chebyshev roots yung may pinakamaliit na L infinity norm. So definitely the error bound using the Chebyshev nodes should be smaller than whatever than the error term or the error bound for any other interpolating polynomial. Kasi guaranteed na pinakamaliit kapag yung x sabays natin ay roots ng Chebyshev. Dun sa pangalawang example, equally spaced abscissas, hindi naman sila yung roots ng Chebyshev. So it will have a larger error bound. Pero again, ito yung worst case. Ito yung worst case. We don't know which is better between them, but at least we know na posibleng mas maganda yung sa Chebyshev polynomial kasi yung maximum error niya ay mas maliit dun sa maximum possible error using equally spaced abscisses. Okay? So I think that's it for now. Sorry, super overtime na naman. Pero any questions? So if I remember it right, problems 1 and 2 sa exercise 1.2 ay about Chebyshev polynomials. So I think after your discussion on Monday, pwede nyo na siyang gawin. Adjust ko yung deadline, maybe give you a couple more days. Probably gagawin kong Wednesday yung deadline. Okay lang ba yun? So sulat ko dito. Lab excerpt 1.2, problems 1 and 2. Okay lang kaya na Wednesday yung deadline? What do you think? 11:59 p.m. All right. And then yung problem 3, which is about the Legendre polynomials. ETBA lang natin muna. Depende kung matatapos natin to sa Tuesday, sa Wednesday. Kasi, yeah, notorious na ako sa ang daming sinasabi sa lectures. So, hindi ko na alam kung kailan ko siya matatapos. But anyway, that's it. Any questions or concerns? Okay, so if none, then thank you for getting up early today and joining us in the meeting. I hope you enjoyed the rest of the day and happy weekend, everyone. So I hope you find some time to rest over the weekend so that you get back on Monday energized for your lab. And let's see each other again on Wednesday. Okay. Bye, everyone.
Thank you po, sir.
Thank you po, sir.